If you grab a standard metric ruler, the physical limit of what you can confidently measure is 1 millimeter. That is the smallest gradation printed on the metal. But the physical world rarely aligns perfectly with those hash marks. When an object's edge falls directly between 2 millimeter lines, your eye hits a biological wall. You are forced to guess the remaining fraction of a millimeter. In 1631, a French mathematician named Pierre Vernier published a method to bypass this visual limitation entirely without relying on magnifying lenses. His solution is embodied in the Vernier caliper. The tool operates as a sliding clamp that leverages a specific geometric offset to amplify tiny distances. The anatomy of the tool is straightforward. You have a stationary main scale and a sliding Vernier scale. Attached to these are lower jaws for measuring outer dimensions, upper jaws for inner dimensions, and a thin depth rod hidden at the tail end. Instead of using optics to zoom in on a tiny gap, the caliper exploits the geometry of alignment. It forces microscopic spaces to reveal themselves to the naked eye. To see how this works, we must look closely at the markings on the sliding Vernier scale and compare them to the main scale. The Vernier scale is purposely mismatched, squeezing 10 divisions into the physical space of exactly 9 millimeters. Because of this, a single Vernier division equals exactly 0.9 millimeters. Subtracting one Vernier division from a 1 millimeter main scale division leaves 0.1 millimeters. This difference is the Vernier constant, or least count, the absolute smallest measurement you can confidently make. By engineering this deliberate mathematical mismatch, Pierre Vernier translated a microscopic 0.1 millimeter gap into a physical, visible offset that a human eye can easily track. Reading this dual-scale system takes 2 steps. First, you look at where the 0 mark on the sliding Vernier scale lands, and you record the main scale value immediately to its left. Second, you scan along the Vernier scale. Because of that 0.1 millimeter mismatch, only one single line on the Vernier scale will perfectly align with a mark on the main scale above it. The number on that aligned Vernier line gives your decimal. If the 4th line aligns perfectly, you simply add 0.4 millimeters to your total reading. But physical tools face mechanical wear and tear. Over time, when you close the jaws of the caliper completely, the 0 marks on the 2 scales might not line up anymore. This diagram shows what happens when the tool falls out of calibration. The middle panel illustrates a positive 0 error. Jaws are fully closed, but the Vernier 0 shifts right. The bottom panel shows a negative 0 error, where the Vernier 0 shifts left, creating a phantom reading. The fix requires no physical adjustment to the hardware itself. You simply identify the 0 error before you measure and subtract that baseline value from your final reading to get a perfectly accurate result. The mathematical logic of the Vernier system is so robust that it provides the exact framework needed to diagnose and correct its own physical flaws. Our modern quest for precision has produced even more sensitive instruments. This is a screw gauge, or micrometer, which uses a threaded spindle to measure objects down to 1,000th millimeter. While digital sensors now offer tighter resolutions on LCD screens, the original analog Vernier caliper remains a standard tool in modern engineering. Because it requires no batteries and houses no fragile electronics, it serves as a bedrock tool in harsh, demanding environments like heavy manufacturing, machining, and aerospace engineering. Pierre Vernier proved nearly 4 centuries ago that the best way to see something microscopic isn't always to look closer. Sometimes you just have to use geometry to change the scale of how you look at it.